Hi everyone, Mr. Lee here. In this video, we are going to go over Newton's second law, but with objects on an incline. Alright, so up until this point, we went over free body diagrams, we went over how to create a net force formula, we went over Atwood machines, and now we are going to go over how objects are impacted when they are on an inclined surface. To start off, I have an inclined surface here with an angle of theta. Once again, we're going to be working primarily off of zero numbers so that you have a backbone, a skeleton for you to work off of in the future. Alright, so here's my scenario. We have an object on an incline. Let's just say for the time being there's no friction, just to make things a little bit simpler. The very first thing that I want to do is I want to create a free-bodied diagram. So the very first force I'm going to draw is the force of gravity. Now look what I did there. I made my force of gravity really big. It went extended beyond the triangle. And this is a technique that I am encouraging all of you to do, because I see so many students make these tiny triangles and it really doesn't do them any good, because it's kind of hard to work with. All right, so make it big, make it go beyond the triangle. And we're going to label it. We're going to label it F of G. That is the weight of the block, also known as the force of gravity. Pay attention to my vocabulary. I'm not calling it just gravity. Okay, it is the force of gravity. And that's because the force of gravity is equal to the mass times the acceleration due to gravity. So there's two gravity things working off of each other. So just calling it gravity, like which one are we talking about, right? We don't know. Okay, so we have that. The next thing, we have this angled surface right here, and because that's an angled surface, we can create a normal force. I'm just going to create my ruler there, and I'm going to try to create there we go, this line right there. Okay, let's put that away. So we have my angled surface, and this angled surface will be my normal force. My angle force for my surface. And remember, normal simply means 90 degrees, and so if we were to extend this out a little bit more, you see right there, that right there is our 90-degree angle. Let's get rid of this ruler. Okay, so we have our normal force and we have a force of gravity. So in terms of a free body diagram, we're done. This is it. But in order to do the math, we need to do a little bit more. Now the next part, we're going to do a free body diagram, but with components. Now remember, please remember, do not add components when they are asking for free body diagrams. Okay, so the very first thing I'm going to show you is the axis that we are approaching everything. So normally, if we were to have an object on a flat surface, we would say that anything along this surface that I drew, that it would be the y-axis, and anything along this surface right here, that'll be the x-surface. But when our surface gets tilted, the axes also tilt with it. Watch this. I will do this in, let's do this in red. So what I mean by that is this surface right here, along this surface, I'm going to do this in red. So I'm just labeling the axes. This is now considered to be my x-axis, because before, when it was flat, the surface represented the axes, and right here, because the surface is angled, that angled surface is my x-axis, and I will do the y-axis accordingly. Alright, so that's my y-axis. Okay, so we have my x-axis and my y-axis. Now, I did that just to show you exactly what we're looking at in terms of axes. Normally, I don't draw it on the paper, but I just do it in like a corner, and I say, okay, this is my x-axis and this is my y-axis. Okay, but I just wanted to show you exactly what I'm referencing to. Next, according to our new axes, our angled axis is anything that does not belong along any of these dotted lines. And so the normal force here, it belongs in the y-axis. However, this weight, this force of gravity, it does not belong in either the x or the y-axis, and so therefore I need to create a component version of the force of gravity. So I'm going to do this in blue. Alright, so the very first force that I am going to draw is my F of G Y. Okay, I'm going to go down, make sure it is running parallel to that. Alright, right there. So what this means is that the force of gravity is holding this object, this mass, against the surface. I'm going to call this FGY. Okay, and it's FGY because it's along this y-axis. Next, let's do this in orange. Next, I'm going to create my FGX. Right there. I'm going to clean this up a little bit. FGX. And you'll notice that what I'm doing right now is I'm erasing that arrowhead because our vectors, when we draw it, it should look like we're creating a triangle because we are creating a triangle. Okay? All right. Okay, so I have my FGY and my FGX. And just as a reminder, this right here, this is 90 degrees. And this right here, between the object, the surface, and FGY and F of G, that right there is theta. That is the same angle as the angle of inclination. Okay, these two angles are the same, thanks to our math rules. Okay, so a couple of things, a couple of tidbits that I want to point out. This is like right down on your paper, you should have something that looks like this. I'm going to show you what students do incorrectly. Okay, so I'm going to create my surface. Okay, cool. And I'm going to create my object. All right, so far, good. Students are good with this. All right, they're going to create their F of G. Good, right? Nice and big because you follow my recommendations. And we're going to create our F of N. All right, and let me show you how students create the components. Okay, do not do this. So they like to create this component and they like to make it go straight down like this. Okay, and then they like to make their horizontal component and they like to make it look like this. Okay, and then they say that this right here is their right angle. Even my program's confused. Okay, that's the right angle. This is not the right angle, and so they're like, "Oh, you're right, Mr. Lee. That's not my right angle. This right here is my right angle." Okay. Well, yeah, visually it looks like the right angle, but that shouldn't be your right angle. Your right angle belongs right here. And then they say that this is theta. So this is like really, really bad. Okay. First off, they're claiming that this angle right here is 90 degrees. Okay, we can't do that. So when you're creating this triangle from these components, it has to look as if it belongs within this new created axis there. So notice here, this orange f of x right here, that doesn't belong in this newly created x and y axes. Now what I mean by that is if I were to redraw my axis, I'm going to do this a little bit bolder because this is an incorrect one, right? So this is my y-axis. Okay, it's good. Like this blue vector, it looks pretty good. It's along that y-axis, and this right here, this is my x-axis. Okay, so if we were to compare this x-axis to down here, you know what? I'm even going to move this x-axis down here just to show you. You see that? You see how this x-axis and this orange axis, I'm going to make this a little bit bolder again. This orange x-axis, they're not even parallel. Like it's not in the same axis. So you can't draw it like I just showed you, right? Please make a conscious effort to draw these components carefully. This right here will always be your 90 degrees. That right there will be the angle, and your components have to line up with the new found axes. All right, so after that being said, I'm just going to clean this image up a little bit so that it's a little bit easier to see. Okay, going to make that a little bit bolder. And here, let's make this a little bit bolder. Okay, so from there, we can create a net force formula. But before we do that, I want to define what is FGY. What is FGX? So let's do FGY first. All right, so I'm going to zoom in here on our angle. Now, FGY, because we have components versions of the forces, we have to be able to redefine them. What is it? So we have a right triangle there, and we have components. Now, if you remember, whenever we have components, we have to use trig functions. So according to this angle theta right here, this theta and this FGY vector, okay, is it opposite or is it adjacent? Hopefully all of us said it's adjacent because it is adjacent. Now, why is this important? Why am I asking this? Because we have sine, we have cosine, and we have tangent. So that's SOHCAHTOA. SOHCAHTOA. Whenever you have a adjacent side, we're using our cosine function. So this becomes, I'm going to make it a little bit bolder for us, f of g cosine of the angle, okay? Because it is adjacent to that theta. And if I take a look over here at this fgx, according to this angle, theta, fgx is opposite of that angle. Therefore, we have f of g sine of theta, because sine uses the opposite. Okay, and f of g, you'll notice that I have fg here and I have fg up here. That f of g is our hypotenuse. So in terms of SOHCAHTOA, that's the h, right? The h right there, the h in the SOHCAHTOA. And it always goes in front of the trig function when we rearrange it. All right, so here we have our equation. And if we were to create a net force formula, same strategies. Okay, let's say we want to do the net force of the x, we say is max. Okay, I'm going to start here, right here. So that's our 12 o'clock, and I'm going to go around the clock. I'm going to go around the clock, and I'm going to look at all the forces. So I'm going to ask myself, does this f of n belong? No, because it belongs in the y-axis. All right, there's nothing over here. What about this fgy? Does that fgy belong? Nope. In the y-axis. What about this fgx? Yes, it does. That fgx does belong and is pointing down to the left because the force of gravity is going to slide this object down into the left, and we say that's negative fgx. And we go back to 12 o'clock and there's no other forces, and so our equation becomes negative fgx equals max. So that is our net force formula right there. I'm going to highlight it. Now from there you can break it down even more, especially if you're trying to determine certain things. We can call it f of g sine of the theta equal to max. We could break that even more because we know that f of g is actually n times g times the sine of theta is equal to max. Okay, so from here, from this net force equation, we can break it down. We can break it down until we're eventually at a point where we're just trying to solve for whatever missing variable we're looking for. All right, so what about net force y? Net force y. Okay, so if I'm looking at my net force y equation, okay, once again, I'm going to start up here at 12 o'clock. I see I have normal force, and it's positive because it's going up. Walking over, fgy. Okay, we have fgy there, and it's pointing downwards because the force of gravity will pull this object downwards. And we have fg sine theta, and we here have f of g. Now, f of g doesn't belong in x or the y, so we're not going to include that in there. All right, and so we have this equation, and that right there, that is our net force equation. We could break it down even more. We can say that, we could break it down and we could say that this is f of n, fgy is fg cosine of theta is equal to may. And we could break this down even more. We can say that the normal force minus mass times gravity, acceleration to gravity, excuse me, is equal to mg cosine of theta is equal to may. Now, let me tell you what. A lot of the times, your y acceleration, this object will not be accelerating along the y-axis. It's probably going to be sliding up and down this x-axis. And so the y acceleration will oftentimes be 0. And so we can finish off this equation by saying the normal force minus mg cosine of theta is equal to 0. And you could even range this even more. You can say that it is the normal force is equal to mg cosine theta. Now this is important. This step right there is very, very important because when we include the force of friction, that normal force comes in handy. Let me show you an example. All right, so if we take a look here, if I have a surface, let's see, yeah, there we go, okay. And we have an object there, we have theta, and let's say, for the sake of this, it's starting at rest. Okay, it's starting at rest, and this object will be sliding down the ramp. Okay, it'll be sliding down the ramp. So the velocity will be going down the ramp. All right, and if I were to draw my free body diagram, once again, start off with my force of gravity, make it nice and big, don't skip that step, and we have my normal force, nice and perpendicular looking to the surface, and we have my force of friction. Okay, we have my force of friction right there. Cool. So we have these three forces, so that's my free body diagram. Now, in order to actually do the math, I'm going to create my component version. So let's do So this in blue. So we have this, going to make it go down. This is my FGY. Okay, notice how I'm drawing the triangles. And here from there, I'm going to go over. This is my FGX. And I know this because this is my vertical axis, and this right now will be my horizontal axis. Okay, and my horizontal axis is whatever the object is sliding down. And this right here, that becomes our theta. Okay, so here we have our component version of this scenario. All right, so if I were to create my net force y equation, I would say we'll start up here at 12 o'clock and then go all the way around. MAY. Okay, we have normal force. Force of friction is in the x-axis. We have FGY minus FGY, minus because it's pointing down. FGX is along the x-axis, and we have force of gravity, which belongs in neither the x or the y. This is all equal to MAY. Okay, and we can say that the acceleration is 0, so we can say that the normal force is equal to FGY. Right? Now we can break this down even more. We can say that the normal force, because if we look at FGY, remember, if this is the angle, this side is adjacent to this angle, and adjacent means that we use cosine of theta. And so we can break this down even more and say it's the mass times the acceleration due to gravity, because that is the equation for the weight, aka the force of gravity, is equal to this equation right here. That becomes our normal force. Right? Now, if we were to do the force of friction version, or excuse me, the net force x version, we have MAX. Force of normal does not belong. Force of friction does belong. Positive because it's pointing to the right. FGY does not belong. FGX does belong. Negative x because it's going to the left, and that's it. All right, so see what we can do here. We know that the force of friction equation is equal to mu times normal force, and then we have FGX, and according to this angle right here, this angle is opposite of that side, and opposite means that we use the sine of theta, MAX. Okay, we can break this down even more. We can say mu times the normal force minus mg sine theta is equal to MAX. All right, now here's something cool that we just found out. If we take a look here, we found out that the normal force is equal to mass times the acceleration due to gravity times the cosine of theta. So we can replace this right in there, so that we can rewrite this as mu times the mass times the acceleration due to gravity times cosine of theta minus mg sine of theta is equal to mass times the acceleration in the x direction. All right, so what I just took you through is a mathematical process, but here's what you need to be able to do. You need to be able to go from step 1 to step 2. Once you're in step 2, this is the net force equation in step 2. The rest of the steps, we're just filtering in the known equations for each part, okay? So that when you finally get to this part, that's when you can actually start plugging in the variables to solve for the equation itself. All right. Now, in the last video, I went over the force of friction, and right now we just covered the force of friction, but I want to show you something very, very important here. So we know that when an object is on a surface, right, we have the normal force and the force of gravity, and we know that the force of friction equation is mu times the normal force, mu, and we can see that all of the force of gravity, the weight is equal to the normal force. All right, makes sense. Now, if we start to put things on an incline, you could try this at home. If you have like a pen or like a book or on a desk, you can start angling the desk, right? There will be a point when you elevate the desk, okay, especially with a book, there will be a point at a certain angle, the object starts to slide down. If you remember from the previous video, when the object starts to move, you just went from the force of friction static territory into the force of friction kinetic territory. Let me show you why this happens. So here we have the normal force and we have the force of gravity, okay, and then we also have its components. Now, if we take a look here, this, let me label this properly, we have the normal force and we have the force of gravity y, and we have the angle right there. So when an object is on a regular surface, the normal force is equal to the force of gravity. However, when we put the object on an angle according to our equations, the normal force does not equal to the force of gravity anymore, right? Because they're not even on the same axis, but rather the normal force starts to equal Fgy. Okay? And we know that Fgy is equal to the force of gravity times the cosine of the angle. So this is true, this statement right here is true even for here. We just know that if there is no angle, this is, let's see, Fg cosine of theta. If there's no angle, that means our theta is 0, and it becomes Fg cosine of 0. And cosine of 0 simply is 1. Okay, so that'd be Fg times 1, which just means that is f of g. So what this shows us is that as we increase our angle, okay, this component right here, this vertical component becomes smaller and smaller. Meaning, so we have an angle right here, and I'm going to do a little bit more extreme. Extreme angle. All right, so we have an extreme angle. I'm trying to draw this properly. Oh my gosh, that is so ugly. All right, so we have an extreme angle, right? So we have f of g, and we have the normal force, like so. Notice I'm drawing it a little bit smaller. Okay, I have my components, and here we go. Oh, that should be straight. Fgx. So this is Fgy. Now, the more extreme our angle becomes, the more vertical our angle becomes, the surface, this is an important part, the surface pushes less. Okay, the surface pushes less, and that's because Fgy is cosine of theta. Okay, Fgy is cosine of theta, and as Fg cosine theta approaches Fg, as it approaches the Fg cosine of 90, okay, this becomes 0. So the closer and closer you get to more and more vertical, the normal force approaches 0. Okay, and we can say that the normal force approaches 0 because this right here is our normal force, and our normal force is equal to Fgy. And we have stated that the normal force and Fgy are equal in this scenario. So what that means is that as this object is on a, let's see, that's a straight surface, that looks pretty bowed, we can say that the normal force is 0 because Fgy is 0. And we can say that Fgy is 0 because Fgy is mg cosine of theta. And when it's straight up vertical, that cosine is 90 degrees. Okay, and so that's because, and like this should make sense in a normal world, right? Like if you get a book, I'm using the book a lot, and you put it, if you put your book against the wall and you release your hands from it, the book's gonna fall, right? Because there's no force of friction holding up that book. And that's because there's no normal force holding up that book, because there is no Fgy component. And if there's no Fgy component, there's no normal force. All right, I'll see you next time. Bye-bye.